Okay, hey guys. So I'm guessing today might be a bit of a lower turnout than normal, I guess because of the midterm or something. But I'll go ahead and write up the warm-up exercise here, which is just looking at some series. Sorry, could you all make sure you're muted? Okay. Yeah, someone's still unmuted. So yeah, maybe I forgot to check the mute people when they come in thing, but I'll try to fix that later. All right, so here's the warm up. Let's see. So it's just to assess the convergence or divergence. So for each of the series, you know, decide whether it converges or diverges. So the first one is the sum of n to the fourth over 2 to the n. The second one is the sum of 2 to the n over n factorial. The third one is the sum of 1 over log of n from n equals 2 to infinity. The next one is the sum of cosine of n over n squared. And then the last one, which is sort of a little bit tricky, is the sum of n factorial over n to the n. Okay, so yeah, let's say we'll resume at 5:15. Okay, so let's go over the warm-up here. So let's see. So what do you guys think about the first series here? Does it converge or diverge?
Converge.
Mm-hmm. Yeah, it converges. What in a few words, what is the reason?
The ratio test.
Yeah, sure. Either the ratio or the root test will give this to you. Yeah.
Oh yeah.
So, yeah, very good. So the ratio or the root test, both. Since we showed like pretty early on in the class, I think that n to the 1 over n approaches 1. So you can kind of like take that for granted if you wanted to.
Ratio test implies the root test works also, right?
Yes. Yeah.
Okay.
Yeah, that's true. But what I'm saying, I guess when I say like you could use the ratio or the root test, I mean that like you can, if you apply the root test, like it doesn't give you something horrible, like sometimes the root test like theoretically does give information, but like the algebra of like the expression you get will be really awful, versus like the ratio test, sometimes it just gives you like simpler expressions. But in this case, like it's not too bad to deal with like this n to the 1 over n, because we already actually dealt with that like early on in the class, I guess. So like this one, for example, I'll just say this one converges. And again, yeah, it's like, the ratio or the root test, but this is, but this is hard, I guess. Using the root test on this, just because, I mean, we actually did in a previous discussion, we did a problem talking about like taking the limit of like n factorial to the 1 over n, for example, or maybe it was 1 over that, or like doing like 1 over n times n factorial to the 1 over n was another limit that we looked at. So like that starts to give you a sense of how you can like deal with the nth root of n factorial, but it's still difficult, I would say, in this case, to like make any arguments about using the root test, basically. But the ratio test makes it very easy, because the ratios here are just like, it's like 2 over n plus 1 or something like that, right? So these converge to 0. So yeah, the ratio test is pretty easy to use here. How about the third one?
Converge.
Okay, so why would you say that?
Oh, I took the ratio test and I said, and then end up with log of n over n plus 1.
Okay. Not quite.
Oh, it's not that. Okay.
Because like you should end up with like log of n over log of n plus 1, which is
n minus. Okay. Oops. Yeah.
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 No worries.
I see what I did.
Yeah, you just can't combine you can't combine the logs this way. And this actually this like approaches 1. So the ratio test actually gives no information in this case. This is actually like a good thing to talk about, because basically there's like some intuition that you can use here to sort of like mentally rule out the ratio test and the root tests as being useful in this case. Because if you think about the function log of n, right? If you think about like how quickly that changes value, basically, it's actually like, so log of n changes like more slowly than, say, like n, or like n squared, or any power of n, really. So like the fact that log of n changes so slowly means that like we already know that the ratio test will give no information for like these functions, so it definitely shouldn't give information for this one either, I guess is what I'm trying to say.
Comparison okay, I see. It can be greater than every 1 over n. Okay.
Yeah. So yeah, you can
Okay.
use the comparison test. Yeah, very good. So ultimately, this should diverge by comparison to the series, the harmonic series, since 1 over log of n is greater than 1 over n for large n, right? Or really, I think probably just for all n, that's actually true. For all n greater than or equal to 2, I think that's true, but it doesn't really matter. All that you need is that this is true for like large enough values of n. But yeah, just to return to what I was saying before, like the fact that like log of n is like less than n for large n is actually not exactly, I mean, that is the reason that this diverges ultimately, right? But that's not the same as like what I was saying before, which is that log, really, like you should just think of log as being a very slowly changing function. Not so much that it grows slowly, but specifically that it's just its value like changes slowly, I guess. Is that's kind of what I was trying to get at. I don't know, it doesn't matter. But I mean, so that is ultimately true that it's like less than n, and that means that you can compare it to the harmonic series, and then that shows it diverges. Very good. How about the fourth one?
It converges.
Yeah, so this one's a little bit like tricky. So how would you justify why it converges?
I wasn't super sure on the test, but like just intuitively, cosine n is like pretty bounded, and yeah.
Yeah. So that's definitely on the right track. Yeah, to do this like carefully, because to do this carefully, what you would really want to show is like you can show that the absolute value of cosine of n over n squared converges, which means that the original one converges absolutely, right? And this one, it's easy to compare to 1 over n squared, right? So here we have, now that they're like all positive, the thing is you can't use the comparison test for like, if you just have a like one series that converges and then another series that's like less than that series, like you can't like directly compare this one to 1 over n squared by just saying like, oh, cosine of n is less than or equal to 1, because like there are a lot of other functions that are less than or equal to 1, like, you know, negative n or something like that, right? Which achieve like large negative values, and that would cause the series to diverge. So it's really the fact that these are all like non-negative numbers in this case, right? And then you can like compare those to this one and say, okay, you know, since these are all non-negative and these are all non-negative, this one converges and is bigger. That means this also converges, which in turn means that this converges because we have a theorem that says like, if a series converges absolutely, then it converges normally, right? Although I think I accidentally left that particular statement out of the lecture. I'm gonna include it in today's, in like tomorrow's lecture or whatever. I will. It's like a very short thing. I mean, it's in section 14 in the book. It's just like a corollary of the comparison test. But yeah, like if a series converges absolutely, then it also just converges normally. Yeah. Any questions about that? Do you guys understand why you can't use the comparison test? Like, it's not valid logic to say that because these are less than or equal to 1 over n squared, then this converges by comparison. Okay, well, yeah. Hopefully.
Wait, Professor, you just said like the reason why we can't use comparison is just because there might be some negative number
Yeah.
for this one, and then
Mhm.
it may cause the divergence, right?
Yeah, in general, yeah.
Okay.
Yeah.
Yeah. So
Obviously,
like uh-huh.
for this particular series, that doesn't end up happening. But like you could come up with another series, like something like, you know, the sum of negative n over n squared, right? This diverges because this is just negative 1 over n, right?
Yeah.
But like negative n over n squared is like less than 1 over n squared, right?
Mhm.
So you can't say that just because this one, the series of this converges, that this series also converges by the comparison test, because it doesn't. That's what I'm trying to say. Yeah.
Oh, okay.
Does that answer your question?
Yes.
Okay, yeah. All right, great. And then what about this last one? Did anyone tackle this?
I said it converges because the limit of when I get like 1 over n times the square root, the n square root of n factorial, and then I think before you said like that goes to 1 over e
Yeah,
or something.
yeah.
So then
yeah.
1 over e is less than 1, so
Mhm.
converges, yeah.
Yeah, that's the right, that's definitely the right logic. I think when I was trying to, I was kind of rushing through the solution to that before, and I think I made it like slightly more difficult than it has to be actually. Yeah, so if you look at the, in this case at least, if you look at the ratios, actually, oh yeah, so in the one before, I don't remember exactly. Oh yeah, we were looking at the ratios. Yeah, we were looking at the ratios in that one too. But then we used that to conclude that the nth roots also approach 1 over e, because the nth root is like stuck between the like lim inf and the lim sup of the ratios. But yeah, so if you just look at the ratios of the terms here, I think what I did before was like slightly more complicated than it has to be. So you get like n plus 1 factorial over n plus 1 to the n plus 1 over n factorial over n to the n. And this equals n plus 1 times n to the n over n plus 1 to the n plus 1, which is n over n plus 1 to the nth power. And this is the same thing as 1 over, or actually, let me write it this way. 1 over 1 plus 1 over n to the nth power. Okay, and then this one, by definition, we just like know that this converges to e, basically. And so this whole thing converges to 1 over e. So the fact that the successive ratios as a sequence, they form a convergent sequence that approaches 1 over e, that automatically means that like the lim inf and the lim sup of the ratios are equal to 1 over e, right? So then, yeah, by the ratio test, because 1 over e is less than 1, this series converges. Right? So yeah, that's just like a little bit of a more, just a little bit of a trickier problem, I guess. I think it's actually on the homework, so you're welcome. All right, anyway. Okay, so how about we do, I think since there's only like 4 of you guys, I'll just make like a room for all of you to just like chat in. And, you know, I mean, obviously that conversation won't get like recorded or anything. So you guys can talk to each other about the problem. Yeah, and we'll take a little bit of time here. So here's a problem that I think is pretty good. So, so show if, and this is based on one from the textbook, but I've kind of augmented it a little bit. So basically these are real numbers. So the series of AN and the series of BN both converge, okay, to real numbers. Then the series an plus bn converges to a plus b. That's the first part. Then the next part is, what about the converse? If an and bn are sequences for which the series an plus bn converges, to series of an and the series of bn converge. And then on top of that, in the converse situation, what if an and bn are bounded? What if an is greater than or equal to 0 and bn is greater than or equal to 0 for all n? Okay, so these two things are variations on this question here, right, about the converse. So basically, and I guess it's kind of giving you a hint that the converse should not be true. Okay, this statement here, if an and bn are sequences for which this converges, then the series an and the series bn converge. This statement is actually false. I'll just say that straight out. But then these two questions are like, okay, if we add more conditions on, or different conditions on an and bn in this scenario, will that force the series of an and the series of bn to converge? Okay, so these are sort of like separate. This stuff here is like, oops, it's only for the converse, not for the original thing. Okay, so yeah, take like, I think 10 minutes is probably good. So, or yeah, we'll say we'll resume at 5:43. Let me make a little sort of chat room thing for you guys. All right, yeah. There we go. Okay, so let's see. So for the first part here, this should be, you know, relatively straightforward, right? Because all we have to do is, you know, to show that this series converges to this limit, we have to show that the sequence of partial sums of this series converges to this limit, right? So, you know, if we say Sn is the sum from, I don't know, k equals 1. Let's just, I mean, we'll just assume for all of these things that the indexing starts at 1 in the series, because that just makes it convenient. So k equals 1 to n of ak, and Tn is the sum from k equals 1 to n of bk. So Sn are the partial sums of the series of An, and Tn are the partial sums of the series of Bn. Then, so if we do that, then basically, right, the partial sums of this series are just the sums of the partial sums of these two, right? So let's say the sum from k equals 1 to n of ak plus bk, right? Which here, this is the nth partial sum of the sum series, right? Then this is just Sn plus Tn. So since we're assuming that both of these sequences, right, the sequence of Sn and the sequence of Tn converge as sequences, Sn converges to A and Tn converges to B, then that means that the sum of the two sequences also converges. That's just a theorem we have from like section 9 or whatever. So this converges to A plus B by, you know, something in section 9 that lets us add limits of sequences, right? So that basically does it for the first bit. Any questions about that? Okay, so for the second part here, what do you guys? Well, so I said this was false, right? Do you guys have a counterexample?
Yes, we're talking about thinking about the sine or cosine. So they may be bounded, and then the sum of it, they may cancel out. However, which like they can converge to a certain limit. However, like each of them, they're not convergent.
Okay, yeah. So like, what would you use as like An and Bn in that example?
An will just be one sine and one cosine. No. Wait, I think sine and cosine works, right? Do they work?
Hold on. I don't think so, because the series of sine of n plus cosine of n, I don't think converges. I think this diverges. Yeah, I'm pretty sure. Yeah.
Like -1 to the n and then plus -1 to the n plus 1 or something.
Yeah, sure. Yeah. You can just do a simple, really simple thing where An and Bn are just like negatives of each other. So yeah, something like An. Actually, what I should have said for the bounded thing is if An and Bn both converge to 0. I mean, it doesn't change anything. But yeah, you could do something like An equals -1. For the first part here, right, you can just say like An is -1 to the n, Bn is like -1 to the n plus 1, right? Something like that. And then like sum of An plus Bn is just 0, because each of these terms is 0, right? But the sum of An and the sum of Bn diverge.
Professor, I wonder, can we use the basis? So like, what if we're using 1 0 0 0 0 and then like 0 1 0 0 0 like this, and then we add them up?
Well, so since we only have two sequences to work with here, if you did like, if An was like 1 0 0 0 0 and then Bn was like 0 1 0 0 0 0, then An plus Bn would end up being 0, or like each of those would converge, I guess, is the problem.
Oh.
as series, right?
Yeah.
Like the series of an would just be 1, and the series of bn would just be 1.
Yeah.
So it wouldn't quite function as a counterexample in this case.
Okay.
Hold on. My phone picks up whenever I say series because it sounds like Siri. All right, anyway. Okay, so yeah, so basically the statement is false in this case, and it's also false in this case, right? Even if you require them both to converge to 0, because you could just make this be like instead of this, you could even just have like an could just be like 1 over n, and bn could be like negative 1 over n, right?
Mm.
So even in this case, you know, both of these two series diverge, but the sum series converges because it's just all zeros. Yeah. So, okay, so that's the first two things. What about this third thing, third condition?
Yeah, then that means it passes the comparison test, and then so it converges. It's less than something that converges.
Exactly, yeah. So in this case, you can say that an converges, oops, just by comparison to an plus bn. And the same thing is true for bn. Right. So in this case, the conditions are definitely strong enough to enforce that, like, if the sum converges, then both of the two original series have to converge. Okay. So yeah, I had one more problem. I don't know if there's quite enough time left for it. Let me think. Yeah, I don't think there's enough time for this last problem here, unfortunately. So I guess, you know, well, I can just, open it up to, if you guys have any general questions right now, you know, we can take the next 10 minutes or so to talk about them.
Oh yes, Professor. I have a question. So like we're thinking about the last statement is true by comparison it to the summation of an plus bn, right?
Yeah.
But like we know that if the absolute value of bn, like by definition, if absolute value of bn is less or equal than an, then the sum of bn converge. But like in this case, how do we know the summation of an plus bn is smaller than the an?
Well, actually, what we're saying is that
no.
Yeah, it's bigger.
Yeah, it's bigger. Yeah.
Right.
I mean, like,
right.
how do you know it's bigger?
It's bigger because we're assuming that an is greater than or equal to 0 and bn is greater than or equal to 0, right? So if bn is greater than or equal to 0, then an plus bn is going to be greater than or equal to an, right? So this here implies an plus bn is greater than or equal to an, right?
Yes.
So so yeah, because they're both greater than or equal to 0, that also makes it so that like the absolute values just don't matter in the comparison test. And of course, like so in the comparison test, you know, one of the series is labeled an and one of them is labeled bn, and then in this case it's like the labeling is slightly different. So really here it's like I forget how they label them in the comparison test. Right, so basically here an plus bn in our problem is like playing the role of an in the comparison test, and then like bn an itself is like playing the role of bn, but then also bn plays the role of bn. So
okay,
yeah. Yep.
And every time when we try to find whether the series converge to a certain limit, we just construct some partial sums of that series, right?
Yeah, at least
That can be a way.
yeah. I mean, that's always a way that you can try to do it. Yeah, and early on, like before we develop any kind of like advanced tools for actually computing series, then like that's sort of the only option you have if you want to actually prove that the series has a specific value, right? Of course, just showing that a series converges is a lot easier. You don't have to know what value it converges to, because we have all these different like tests and stuff that you can do that'll just tell you when a series converges or doesn't converge, even when you don't know the value. But if you're talking about actually proving that it has a specific value, then yeah, for now, it's sort of like you just have to hope you can find like a formula for the partial sums. But later on, like it will eventually become the case that some series where there's no like nice formula for the partial sums, you can still prove what value they have. Like for example, this one actually from the Warmup, this series here, you probably even know what the value of this should be. This is E squared, right? And that's because if you take the Taylor series of e to the x, that's like the sum of x to the n over n factorial. So if you just plug in x equals 2, you get that this series equals e squared. So that's just like some weird, it comes from a more advanced like theory, but we don't really have the tools to do that kind of thing right now. Yeah.
Will we do that in this class, like to find out?
Yeah, I mean, we'll eventually,
okay.
yeah, we'll eventually define. I mean, actually, I think the way we do it is like, I think we just kind of declare by fiat that like.
From like the Taylor series.
Actually,
So.
no. Actually, no. I think e to the x is defined separately as like just an exponential function with the base e. But then, yeah, we will like develop Taylor series. So it will be like e to the x will have its own definition, and then I think we'll show that the Taylor series is like x to the n over n factorial, something like that. We'll see. But yeah, I mean, we do talk about Taylor series eventually, so yeah.
What about like the base, like the pi squared over 6? Can we like, will we be able to like prove
that
at the end of this class?
That's like a different thing, yeah.
Okay.
It's from like number theory and stuff, yeah.
Oh, okay.
Yeah, the proofs, there's some pretty cool proofs of that, but they're like kind of involved, yeah. So anyway, but yeah, that's actually, so that like values of that thing, this is kind of cool, like trivia, but this series of like 1 over n to like, usually people use the letter s, that's actually what's called the Riemann Zeta-Function.
That's like the $1 million problem, right?
Yeah. It's one of the like, well, it's part of that problem. Yeah, there's the Riemann hypothesis is like one of the most important outstanding problems in math, and it's a question about this function. At least this is how you can define it for when the real part of s is like bigger than 1, I think. So then you can like extend the definition to other numbers, but yeah. So if s is a real number bigger than 1, then that's just like a special value of the Riemann Zeta function.
So is it always convergent if
except for
1, I guess?
Yeah, and yeah. That's actually the only pole in like the entire plane, I think. So
if we're doing a comparison test, we can just assume 1 over n cubed is convergent, 1 over n fourth is convergent.
Yeah, well, so you can show that. Yeah. You can show those series converge without having to like compute their values, basically. So like the integral test is the most common way to show that these values converge when s is a real number. Hold on. So this is for all of C except S equals 1. So if S is a real number and S is greater than 1, then this series converges by the integral test, which is going to be in like tomorrow's lecture. So you'll see why this converges, even though we haven't technically defined what an integral is. I'll talk about this in the lecture a little bit, but like you can sort of think of the integral test for now as just being like this sort of a heuristic tool that lets us tell whether a series converges or diverges without necessarily giving us a way to like rigorously prove that the series converges or diverges, at least using what we've done so far. But you can still use it to like tell, right? To tell when a series converges or diverges, basically. It's still valid to use. So yeah, the integral test tells us that these series converge. And I think you can actually, in some cases, you can even use the integral test to formulate a proof for the convergence of these series that doesn't actually rely on the integral test, because you can use the integral test to come up with like different bounds, basically. You can come up with like bounds for the like partial sums, basically. Yeah. You can come up with like bounds for the partial sums using the integral test, and then you can just use those bounds and pretend that you didn't get them from the integral test, basically. And you can just prove that these converge directly that way if you want. And I don't know, yeah. So that's the gist of this. Okay, well, it's 6 o'clock, so I got to get going. But
Thank you so much.
Yep, thanks for coming, and yeah, hope to see you guys tomorrow.
See you.
Thank you.
Thank you.
See ya.